All right, so let's start chapter 10. You ready? This is one of my favorite chapters too. I like all this stuff, but chapter 10 is really cool. All right. So we've done ionic bonding models with lattice energy and that kind of stuff. We've done Lewis theory, which is a covalent bonding model for the most part. We talked about bond energies. So with chapter 10, where it takes the baton from chapter 9, is it says, well, we've got Lewis theory, but what are the shapes of molecules from the Lewis theory, and what are the bonding models we can use to explain that? Okay. So we'll talk about molecular shape, which is really what VSEPR is all about. Oh, by the way, this is a typo. It should say VSEPR, not PER, but we always say VSEPR, just, you know, it becomes that. So change this to VSEPR. Okay. We'll talk about molecular polarity and dipole moments, and then we probably won't get to this today, but we got to talk about valence bond theory and molecular orbital theory. All new stuff for you to chew on. So, okay, so we've done Lewis structure, but Lewis structures are two-dimensional structures. Okay, they're flat on paper. But what we need to start doing is thinking about molecules in three-dimensional shape. So molecular shape matters. Okay, for example, I don't know why I keep mentioning drugs, but drugs are a really nice example of how shape is really important in general. Many interactions to drugs in our body are geometry specific. How do drugs interact in our body? Well, we've got neurotransmitters, and that's one thing. Okay, but when we have a drug that metabolizes in our system, you've got enzymes in our body. The enzymes are huge molecules. They're big biomolecules. They're polymers of amino acids, and they fold around substrates, and then they react on them. Okay, and the chemistry involved in that is typically acid-base chemistry. The amino acids in your proteins, which are enzymes, have acidic or basic properties. Okay. And so, but the way they fold around substrates, i.e. drugs, okay, is geometry specific. Okay, so I'll show you an example of that. So the effectiveness of how that interaction takes place affects the ability for the drug to have its therapeutic benefit for us. Some drugs inhibit the effectiveness of other drugs. So for example, if you take biochemistry, you'll learn that you've got inhibitors versus activators. An enzyme is such a huge compound that even though it has this active site where it folds around a substrate, there might be some other site in the molecule of the enzyme where we call it a regulatory site, where some other substrate or competing drug can come in and prevent the protein from folding around the substrate that you want it to fold around. You know, it's kind of like I'm about to hug somebody and they stop my arm, you know, and I can't do it anymore. Okay. And that's, again, geometry specific. Drug compounds have this geometry issue. Okay, so a lot of time, and I have your dollars, is spent on drug purification and analysis. Okay, purification analysis. Here's an example of a drug. How many of you have ever heard of omeprazole? Yeah, that's what I thought. Okay, nobody's ever heard of this. Okay, but this is the active ingredient in a brand name drug called Prilosec. You ever heard of Prilosec? Anybody? Nobody's ever heard of Prilosec? Nobody. Okay, almost not anybody. I've heard of Prilosec. One person, that's it? Okay, Brittany, you've heard of Prilosec. Okay, so Prilosec is a antacid basically, but it's more than an antacid. It's what we call a proton pump inhibitor, meaning that it actually prohibits the production of hydrogen ions in your stomach from becoming abundant, because when we have a lot of hydrogen ions in your stomach gets really acidic and you get heartburn. Okay, so this is a proton pump inhibitor. It prevents basically HCl buildup in your stomach. Okay, when you look at this drug, okay, you'll notice that it looks kind of like the molecule has two images looking at each other. Okay, so imagine this red line is a mirror, and this drug is looking at itself in the mirror. Do you see that? Okay? So when we get to VSEPR, okay, you might remember from Chem 107, we've got wedges and we have dashes. Do you remember that from Chem 107? No? Well, if you don't, you'll remember it now. Okay. So the wedge is a bond coming out of the plane of the board. A dash is a bond going into the plane of the board. A straight line is just a bond on the plane of the board, okay, or on the plane of the wall here. So you can see how this wedge, or excuse me, you can see how this dash is kind of looking at that dash, and you can see how this wedge is coming out on that wedge. It's sort of like looking at itself. Okay, maybe everybody on this side of the room, raise your left hand. And everybody on this side of the room, raise your right hand. And then look at each other. See, that's what's going on there, right? Now, if you tried to stack yourselves in a stack of bodies, would the left hand overlap with the right hand if you made a stack? And the answer is no, it wouldn't. Okay? Can you perfectly stack your feet? You've got right-handed and left-handed feet. You've got left hand and right hand. Can I stack it? No, I got the thumb on this side, but I've got the thumb on this side. I can't stack these. Maybe if I flip them this way, though, now they're mirrored images. This thumb is looking at the back of this thumb. Do you see that? Hey, hand. Hey, back of my hand. Oh, I'm looking right at you. Okay? But if I tried to stack them both face down, they wouldn't stack. Okay? And so a lot of compounds have something called right-handed and left-handed forms. We call that chirality. Okay? And you'll learn, if you take OChem, OChem Part I, you will learn about chirality. Okay? It turns out that chirality is really important, though. It turns out that we can only metabolize one form of the drug, but we cannot metabolize the other one. And so we have enzymes in our body that can actually convert this form into that form, for example. However, okay, there's actually about 10% of the population that does not have the genetic material to produce the enzyme to convert this into that. Okay, and so what happens, when you take Prilosec, you're actually consuming both forms of these drugs. What AstraZeneca, the drug company that makes this drug, did is they said, well, we see a money-making opportunity here. We know that there's 10% of the population that cannot convert the non-usable form into the usable form. Let's make another drug by purifying one form from the other and only putting the usable form in a tablet, and we're going to call it Nexium. You ever heard of Nexium before? Maybe, maybe not. A couple of you are nodding yet. Seen it, heard about it. Okay, and so how do you do that? Well, so in my work in industry as a chemist, okay, I worked on developing methods for separating one form from the other using chromatography. Okay, and so what they do is they say, well, let's look at these drug compounds as a function of time. This x-axis is minutes. And we say, well, if we can collect fractions out of this plumbing, all this liquid coming out, if we can collect fractions over time, and maybe collect one compound in one fraction and the other compound in the other fraction, and then just isolate the two from each other, blow down the solvent into a powder again, and then repack into a tablet and call it Nexium, that's a lot cheaper than to synthesize a whole new drug from scratch, go through all these clinical trials and all this stuff. Right? I mean, they still have to do clinical trials, but the clinical trials are a slam dunk when the drug's already known to work. Right? So, so it turns out, how much money do you think a drug company makes off of a drug? Like billions and billions and billions of dollars, right? So if we didn't have this difference in molecular shape, which is what this chapter is all about, if we didn't have this difference, we couldn't separate drugs from each other based on shape. We couldn't make billions of dollars off of you and me, okay, if we didn't have this difference in geometry around a central atom. Okay, and so that's why molecular shape matters. That's why it's important. Okay, it's like billions and billions and billions of dollars important. Okay, so the material, what this came from is you've got a column with material in it. The material separates compounds based on differences in polarity. The polarity differences come from differences in geometry, differences in shape. Okay, and so that's how this happens. Also, there's maybe a little bit of impurity in there too. These are impurities that they don't want in our products, right? So we can get those out of there too, right? So drug purity, drug efficacy, it all comes down to molecular shape. That's why it matters. All right, so you ready to learn about molecular shape, at least on the fundamental level? All right. Okay, so molecular geometry, refers to the 3D structure of a compound. Central atoms are surrounded by other atoms, or they're also surrounded by lone pairs, okay, of electrons. The shape of molecules are related to geometric figures. If you think of the geometric figures having corners where the atoms reside, you can come up with structures like tetrahedrons and trigonal planes and things you might remember from Chem 107. And these different shapes have different bond angles too. Okay, so Lewis structures are two-dimensional compounds, or two-dimensional representations of a compound, but they don't take into account the shape. However, Lewis theory does predict how many electron groups are around the central atom. Okay, so notice how I have the word there, electron groups underlined. Okay, an electron group refers to an atom that's bonded, an outer atom, or it also refers to a lone pair of electrons. So electron groups are always negatively charged, and this has to do with Coulomb's law and then the shape. So this gets us to VSEPR theory. Okay, so valence shell electron pair repulsion is what VSEPR stands for. It's an acronym. The basis of VSEPR is to maximize the bond angles between neighboring atoms to a central atom. Okay, if I have this compound here, the idea is to maximize all the angles as best we can. What makes up this bond? We have an atom, an electron, another atom, right? We've got electrons being shared here. Electrons are negatively charged. These are negatively charged. These are negatively charged. These are negatively charged. And so are these. They hate each other. They want to get away from each other as much as possible. So what is the most efficient shapes we can come up with to maximize the angles between these outer atoms that are all bonded to the same central atom? That's what VSEPR is about. It's about maximizing these angles. Okay, now there might be, instead of a bonded atom, you might have a lone pair. Okay, the lone pair also repels all these other bonds. Okay, so electron groups are essentially bonded atoms or they're lone pairs. Okay, VSEPR maximizes the bond angles between electron groups or lone pairs. Yeah.
What do you mean by maximize?
Maximizing a bond angle. So basically getting this guy as far away from this guy as possible. That's what I mean by maximizing. I'm maximizing the angle between these two. They're both negatively charged. They want to get away from each other as much as possible. But maybe you got this angle here, right? But then you've also got this other atom over here, and he repels both of these two, right? So at some point, all these outer atoms have to take on a shape that maximizes the angles collectively throughout the whole molecule. That's what VSEPR is about. It's about how can we find the most stable structure to minimize these repulsions between neighboring electron groups. That's what it's about. Okay, so that's why they call it valence shell electron pair repulsion. Okay, here's just a schematic. Here you got the bonds. These are all repelling each other. These electrons here repel these guys, right? Okay. So electron groups, as I was saying, can be either a single lone pair of electrons or a bonded atom. What if you have a double or triple bond? It doesn't matter. It still counts as just one bonded atom, and so we just count that as one electron group. We have something else you should know called the steric number. Okay, and that's the total number of electron groups on a central atom. Okay, steric number, steric number is the number of bonded atoms, and I would add a little extra to this, and I would write number of bonded atoms to the central atom, okay, plus the number of lone pairs directly on the central atom. Okay, this is all about center atoms, right? Not outer atoms, but we're talking about atoms that are in between other atoms. Okay, so number of bonded atoms directly on central atom plus number of lone pairs directly on central atom. Okay, and you add those two together and that gets you the steric number. And we use the steric number to determine the shape of the compound. Some other geometry terms you should know of. Once you have the steric number, you can figure out what the electron geometry would be. That's the shape of the molecule just based on the bonded atoms and lone pairs. But then we've got the molecular geometry, also called the molecular shape. Okay, and that's the shape of the molecule when not taking into account the lone pairs. All right, when you're just looking at the atoms themselves and what shape they make. Okay, so I'll get to that in a minute. There are two things that affect bond angles. Okay, you have the different size of atoms on the outside, and those will differ in the space they take up. Bigger atoms will repel its neighbors more than smaller atoms will. So if I have, say, an iodine atom here, but I only have two fluorine atoms here, the fluorine atoms are going to get pushed together a bit more by the big iodine atom. Okay, for example. Double bonds also repel more than single bonds do. Right? They take up more space. Okay, and then lone pairs take up a lot of space. Okay, they're considered even bigger than bonded atoms. So here's an example of that. Here's formaldehyde. If you look at the bond angles, you would think that all three of these bond angles would be 120. You would think. But because of the double bond taking up more space, it pushes these two hydrogen atoms closer together. So instead of being 120, it's less than 120 down here. But it's actually more than 120 up there. All right, so double bonds take up more space. And also lone pairs take up more space. All right, so water normally is H2O, right? Okay, these normally should be, for a perfect tetrahedron, 1 to 9.5 degrees. But it turns out that the bond angle, HOH bond angle, is less than 1 to 9.5 because the lone pairs on the water end up kind of squeezing these two hydrogen atoms closer together. All right, the lone pairs take up a lot of space. So two things that affect bond angles: lone pairs and double bonds, or a big atom. Okay, we'll also distort the bonds a bit, distort the bond angles. So these two factors: lone pairs, size of the bond, or size of the bonded atoms. Okay, so the way to predict the shape of a molecule is to first draw the Lewis structure, determine the steric number, classify it based on the steric number, and then you do that using the VSEPR table. Okay, so you should have a packet, or not a packet, but a sheet that looks like this. So you've got categories of electron geometries. In Chem 107, you only did these first three in Chem 107. But in Chem 111A, we add a couple more onto this list. So we've got linear compounds, we've got trigonal planar compounds, tetrahedral compounds, trigonal bipyramid compounds, and octahedral compounds. The wedges and the dashes represent bonds coming out or going into the plane of the paper. So for example, this is a trigonal bipyramid. This represents this shape right here. Okay, so I'm going to stand, this is the plane of the board, or plane of the wall. I've got this wedge, which is a dark wedge coming out at you. All right, so this dark wedge here, it gets smaller and it gets bigger. It's going from small to big. Okay, if this bond is kind of looking at you, it's getting small, and as it gets closer to you, it's getting bigger. Okay, and then you've got the dash, which starts big and then gets small, because it's now going away from you. Right? Things start to look smaller to you as things are moving away. All right, so that's this bond right here. Okay, so this atom here is this dot. This atom here is this dot. This atom down here is this dot. And so together they make a plane. Here's the bond coming out of the plane. Here's the bond going into the plane. Can you see the dashes and wedges and how it relates to this? Okay, here's a octahedron compound. Okay, this has 6 bonded atoms to the center. okay, or a lone pair. Alright, so I've got this atom here is this dot. This atom down here represents this dot. And you got two wedges coming out at you and two dashes going into the plane of the board. So the plane of the board is right straight through. So for those of you over here, you're looking at it this way, right? Here's the plane of the board, two wedges, two dashes. And then these atoms are in the plane of the board. You see it? If you give them these big models and you have a sibling, you want to wake them up in a really obnoxious way, you say, "Wake up!" And just like stick the molecule in their face. Whoa, whoa, whoa. Okay, wait a minute. Okay. So the bipyramids and the octahedrons are the higher order structures that we're tacking onto the Chem 107 structures that you've already seen. So I'm really anal about this. Wedges, I'm going to ask you to draw these. Okay. Wedges are dark and they get smaller and they get bigger as they go away from the essential atom. Dashes get big and then they're smaller as they move away from the atom. Okay, I'm really, really particular about that because I want to know if you can visualize molecules in 3D. And it's easy for some people and it's really hard for other people. Okay, it depends on just how your brain tends to work. Okay, so the better that you can do this, the better off you'll be when you get to organic chemistry, if you take organic chemistry. I teach this class as if I expect you to take organic chemistry because my class is so engaging and so fascinating studying this stuff in Chem 111A that you just say, oh, I've got to take more chemistry beyond Gen Chem. Okay, so if I don't get you there, I tried. So, but anyway, but I teach the class as if you're going to use this stuff in organic chemistry. Okay, so here's those shapes in the VSEPR table. And this is how you do the Lewis structure, okay? And then you look at the steric number based on the Lewis structure. So the steric number is just off to the left here. Now on your sheet, I believe you have the number of bonded atoms and lone pairs that add up to these numbers. All right, you should see that, okay? So you can see how adding the number of bonded atoms to the central atom plus adding the lone pairs on the central atom together will give you a steric number. And then based on the steric number classification, you've got the different electron geometries. Now within the different electron geometries, based on the number of lone pairs that make up the steric number, you've got a different molecular shape that is within the broader category of electron geometry. So for example, if I have a trigonoplanar compound, if there's one lone pair on the central atom, we actually call that bent for the shape. Okay. If I take, here's a trigonal bipyramid, if there's one lone pair on the central atom, we call that a seesaw. Okay. So how do you get a seesaw shape from that? Okay, so here's a bipyramid, right? If I take a lone pair, or if I take an atom off and replace it with a lone pair, it's like a seesaw. Okay, so that's where these names come from. Okay, if I took off another atom and replaced it with a lone pair, we call it a T shape. See how it makes a T? And so that's where this T shape comes from. So every time you take off an atom and replace it with a lone pair, it's going to give you a different shape. Okay. If I add 3 lone pairs on a bipyramid electron geometry, I get a linear compound. So this is linear now, right? It's just 3 atoms in a line. Okay, so we still consider this molecule, even though you don't see the lone pairs in here, we still consider this a trigonal bipyramid electron geometry, but we say the shape is linear. Okay, and so you'll have to pay attention to the question. Is it asking me for the electron geometry, in which case we're including the lone pairs? Or if it's asking me for the shape, it's asking you what shape do the atoms only give you? Okay. So this is linear, right? But even though there's still lone pairs all around here, making it a steric number of 5, still a trigonal bipyramid electron geometry category. It's just that now it's the linear shape, right, within that category. Okay, so, okay. So every time you take off a lone pair, you get a different shape. Or excuse me, every time you add a lone pair, take off an atom and replace it with a lone pair of electrons, you get a different shape. Okay, so where do lone pairs go? Okay, it turns out that it depends on where you put the lone pairs in order to maximize these bond angles or angles between electron groups. If you have a linear, trigonoplanar, or tetrahedron electron geometry, it doesn't matter where you put the lone pairs. Okay, if you take off an atom and replace it with a lone pair, it doesn't matter which atom you take off. Okay, but for trigonal bipyramids, and I just kind of did this in front of you a minute ago, it does matter where you add the lone pairs. So for a trigonal bipyramid, we call these positions, we call them equatorial positions. And then these ones that I don't have circled, these are called axial positions. Okay, so here's a bipyramid again. Here's planet Earth spinning on its axis. Okay, you see what I'm saying? Axial positions are what the axis is spinning on, right? Or it's spinning, or the molecule is spinning on an axis. Okay, and then you've got the equatorial positions, which are analogous to planet Earth if you're near the equator, you know, which is spinning around, right? Okay, so it turns out that when you put lone pairs, if you had a lone pair on an axial position, let's just say you have this lone pair and it's big and it's taking up all this space. Okay, you've got 90-degree angles between the one lone pair and these bonded atoms. Okay, so let me draw a picture of this. Alright, so here's, if I have this big lone pair of dots there, okay, okay, so this angle would be 90 degrees. This angle would also be 90 degrees. Okay. This angle here would also be 90 degrees. Okay, but we don't like that. Okay, what's better is if you can say, okay, what if we can draw this to where the lone pair now is like this. Okay, so now we only have two atoms that are 90 degrees compared to the lone pair. Okay, and by doing that, we now increase the bond angles over here. Okay, so so these are all this bond angle between these two guys is 120. This bond angle here is also considered to be 120. Where am I getting these bond angles from? So if I look at this, if you're looking down the molecule axis, 120, 120, 120. Okay. 90, 90, 90 angles, 90, 90, right? These are all 90 between the axial and the equatorial. Okay. So for a trigonal bipyramid, it's better to have the lone pairs be put on an equatorial than it is on an axial position. Right. We want to maximize the angle between the bonded atoms and the lone pair, which takes up a lot more space than the bonded atom. Okay, so to minimize, so here where we shouldn't have it is to have three 90-degree angles, whereas in this one we only have two 90-degree angles, where we're actually decreasing the number of close angles to this lone pair. Okay, and that improves the geometry. Right, makes it more stable, makes the molecule more stable. All right. On the other hand, for octahedrons, we do the opposite way, right? We put lone pairs on the axial position instead.